Hello and welcome back to mathematics. In this video I'll briefly go over the trigonometry script and fill out the script with you, or you can just watch it. If you want to skip to a specific chapter, you can use that using the chapter function on YouTube. The chapters should be indicated. All right, let's dive right in with the first chapter, the prerequisites from the quarta. You should still know about right-angled trigonometry. And in this setup here, you should remember that, for instance, sine of a particular angle is opposite over hypotenuse. So I'm just going to fill this out here. Sine of alpha is going to be b over, c. Tangent of alpha is opposite over adjacent, so here b over a. Cosine of beta, here you have to adjust to the angle, so here the angle is beta, so be aware that cosine being adjacent over hypotenuse, you really have to take the adjacent of beta now, not alpha, so that plays an important role. So here cosine of beta is b over c, so the adjacent of beta is b. And cosine of alpha, on the other hand, you'll realize that this is a over c. Sine of beta, now the opposite of beta is a, and you just put that as a over c. And tangent of beta is opposite over adjacent again, and in this case it's a over b. Here you can play around a little bit yourself. What you should realize is this special connection or this relationship between here between sine, cosine and tangent. It works for alpha or it works for beta, of course, but the important relationship is that tangent is always sine over cosine of the same angle, of course. This only works if you put alpha in every function or in every trigonometric ratio. So it's not that tangent beta is something with sine alpha and cosine alpha. You could do that too, but it's not really necessary. All right, then we jump to chapter 2, measuring angles. So here I prepared this little discussion that you might remember from the lessons. The full rotation usually in everyday life corresponds to 360 degrees. The possible reasons here are that 360 contains a lot of divisors. So 360 degrees is divisible into many different angles, and those angles are then themselves and not decimals. So here that are not decimals. The cool thing about this is that you can then divide it up into many different smaller angles. So 360 you'll realize is divisible by 2, 3, 5, 6, 10 and so forth, and that is useful to then talk about smaller angles. So then the question is begged, what would be another candidate for a full rotation? Of course, you could take 720, 1080, stuff like that. Very possible. There is one mathematically motivated candidate numbers, and that is 2 pi. And we're going to explain in a moment why. So new one full rotation is 2 pi. The reason for here, you might already remember that one full circle is 2 pi times the radius, and if you fix the radius to 1, you get exactly 2 pi. So this we discussed here. So I'm gonna come to the definition of radian in a moment. First, I wanna make this transition that here, if you fix the radius to be 1, and you say, okay, a radius of 1 gives me my circle sort of where I measure the angles. So imagine you're sitting here at the center, and then you turn by, let's say, this much. Then you have another radius of 1 here, and then you just measure, okay, what fraction of 2 pi is that? You could, of course, take another radius than 1. You could also take 5 and so forth. It's just that then the full rotation here would be 2 pi times the whatever radius you choose. And if you choose, for instance, 3, the full rotation would be 2 pi times 3, so 6 pi. Would work equally well. Historically, people just agreed on a radius of 1 because it's the easiest number. And here, what we're going to do is we're going to really equate or correspond rather 360 to 2 pi. So this wavy thing here, you can read it also as an equal sign. It's technically not really equal, but you don't make any mistake if you treat it as an equal sign. I'm just trying to be as precise as possible here. And then with this 360 is equal to 2 pi thing, you can make a number of sort of conclusions that 180 is pi, 90 here is pi over 2, 45 degrees is pi over 4, and so forth. So here you can have a go at exercise 2.1, or we solve that together in the lessons that you convert from degrees to radian or back. Very important here on the calculator, always make sure that you have your calculator in the adequate mode. If degrees are asked in a certain exercise, radian if it's about radian. All right, so now going back here to the definition of a radian, what actually 1 radian is if you take on a given circle, you take your radius and you put it out this exact distance of r, you walk that, so to speak, on the circle, then the angle that is being formed is equal to 1 radian. For the purposes of the exercises, you don't really need to keep this fact here in mind. It's just important to have heard it once and to know the definition. Okay, once you're set up with radian, you can jump to the unit circle, and the unit circle allows us to generalize sine, cosine, and tangent to angles larger than 90 degrees or pi over 2, you see here. Up until now, note that we could only handle angles below 90 degrees because we've already spent 90 degrees on our right-angled triangle, or on our right angle in our right-angled triangle. And what we do here is we just take any point P on a circle that has radius 1, and we place that in the coordinate system. And that means that here, this distance here is just a distance of 1. And what we're going to look at or concern ourselves with is what is the y-coordinate of this point and what is the x-coordinate of that point. And what we also going to agree on is that we measure angles in the unit circle, so attached to every point here somewhere on the unit circle is an angle, and we measure this angle going from the x-axis counterclockwise. So this here would be the angle, let's call it alpha, attached to this point. So if you had a point, let's say over here, then the angle attached to this would be this here, for instance, and so forth. So all the way to 360 degrees. So if you have a point here, the angle would be this one here. Yeah. Whether you measure the angles in radian or degrees. Doesn't really matter. If you want to be really precise, you would measure them in radians, but for the purpose of being intuitive, we're also going to use degrees a lot. So with this knowledge in mind, you can fill out this unit circle here. I won't do this here because we did that in the lessons, but please consult your script or do it again for this unit circle to see which angles are. But it's fairly intuitive. I mean, you just continue. Here is 0 degrees, here's 30 degrees, meaning here is 45 degrees, 60 degrees, and so forth. All right, now I will look at the important connection between the unit circle, sine and cosine. So if you have the unit circle like this again, you have your radius here, that's also equal to 1, and we said we wanted to look at our y, and we wanted to look at our x here. What you should have found out here with the unit circle, or we did find out, is here that always for the location of the point, you have the, what did I put, the x-axis in blue, or sorry, the x-coordinate in blue, the y-coordinate in orange. And this here is always the sine or the cosine of the angle. So here this is sine of 30, or if you have the calculator in radian, this is sine of pi over 6. Same for the other value here. This here is cosine of 30 degrees, or it's also equal to cosine of pi over 6 in radian. And this means that in general here, y is going to be sine of alpha, if our measured angle here again is, as we previously agreed, alpha, and the blue line, the x value, is always going to be cosine of alpha. And this helps us a lot to firstly note that we've now generalized sine and cosine to more than 90 degrees. So if we, for instance, say, I don't know, I want cosine of 100 and maybe 20, maybe that's up until here, roundabout. You choose this point that corresponds to 120 degrees, and then you go down to the x-axis like this, and you join the triangle. So this here would be cosine of 120 degrees, and the orange one would be sine of 120 degrees. So that's how you find out angles with, find out cosine and sine values with angles in the unit circle. And the one obvious thing is that if you have alpha, you can also generate this point a little bit, maybe in a silly fashion, maybe like this. Here you do add a one whole 360 term. So this here would be 360 plus alpha, or in radian 2 pi plus alpha. And then you realize you get to the same point, so the sine values and the cosine values will stay the same. So in equations, you would say that sine of alpha is the same as sine of alpha plus 360 here. And same for cosine of alpha is cosine of alpha plus 360. So for instance, sine of 10 is the same as sine of 370 degrees, and so forth. And the same in radian. So basically you do exactly the same thing, just delete the 360 and put 2 pi here. So if you measure in radian, going a full circle is 2 pi. All right, once you know your way around the unit circle a little bit, you can look at different symmetries. What I mean by that, if we look at the sine, so again, I take here a point. Let's do the same thing as before. You connect this one here, 1. We have our angle alpha that corresponds to our point, and we have our vertical sine of alpha and our horizontal cosine of alpha. Now I'm gonna just focus on sine of alpha. You'll see that here what you can do is you can ask yourself, well, where do you have the exact same height, in the sense of, is there another triangle in this unit circle that gives you the same height or orange height sine of something else? And yes, there is. What you can do is you can just transport or just do a horizontal line and go over to here. And then this produces another point. And I do exactly the same unit circle construction here, like this. Again, 1. And now this here has the same orange height. So here, you might remember, you might see it directly, otherwise pause the video briefly and try to find out what do I have to put here, if you think in degrees, into the brackets in terms of the angle. So here the angle is 180 degrees minus alpha, or in radian sine of pi minus alpha. Because you go, 180 degrees, and then you go alpha back, basically. So 180 minus alpha or pi minus alpha. And that here is the symmetry for the sine, that you say, hey, okay, for the sine in the unit circle, or in general, sine of alpha is the same thing as sine of 180 degrees minus alpha, or sine of alpha in radian is the same as sine of pi minus alpha. This is important because, you find often one solution with the calculator and the other solution you have to calculate yourself. So let's say in a particular problem you find out that alpha is 30, well, then the other solution would be 180 minus 30 would be 150, and you have to find that yourselves. Same thing with cosine. Here you just do the same construction, but you focus on the cosine. So again, here our construction with alpha, and this time I will just focus on the cosine. So yes, here you have the orange sine, but we'll focus this time on the cosine. Here again, try to think about where is the second cosine value that is the same and what is the angle. And here this time you go vertically down, and then you generate this triangle here. And note that here we have to go all the way around up until here. Again, think what this could be. And this here is just 360 minus alpha, or 2 pi minus alpha. So from that we know that cosine of alpha is the same as cosine of 360 minus alpha, or it's in radian, cosine of alpha is the same as cosine of 2 pi minus alpha. Those are the two important symmetries for sine and cosine. All right, then we jump to the trigonometric functions. We used that in class to generate the graphs of the trigonometric function, or we looked at this in this chapter. Here, again, if you want to go through it yourselves, try to enter those values. Here I gave you a coordinate system in radian, and what you find out for the sine, sine of 0 is 0, sine of pi over 2 here is 1, then sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0. So you have the familiar sine curve here, like this. And this would just go on and on and on to the left and to the right. Same thing or same strategy for cosine. Cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, 3 pi over 2 gives us 0 again, and 2 pi gives us 1 again. Then generates this curve here, like so. And again, it will go on and on and on. What you can rediscover here from before is that, for instance, if you now have an alpha, let's say this here on the x-axis is my alpha, generates this sine value here, maybe a little bit more than 0.5, and this here, before in the unit circle I use green, this here actually is the same sine value as this one here. And you'll realize, here for the second one, I have to go to pi and back by alpha. So you've rediscovered the symmetry of the sine in the graph of the function. Same here for cosine. Let's say our alpha is here. Then this generates this cosine value, and you can put that over here, and then you realize here, what is here? Well, here is exactly 2 pi minus alpha, or if you put degrees on the x-axis, 360 minus alpha. And that rediscovers the cosine symmetry again in the graph of the cosine. A little bit trickier is the graph of the tangent. Here you got to remember that tangent is sine over cosine, and if you divide by something such as cosine of x here, you always have problems when you would divide by 0. Cosine of x is 0 at the following values. We know here at pi over 2 and 3 pi over 2. And those sort of creates, intuitively you can say this creates sort of no lines where you're not allowed to cross. The fancy mathematical terms is those are asymptotes. Then you can plug in a few values. You can again sort of play with the different values. There are other ways that we looked at in the lesson together. What you always should be able to generate is that the tangent looks like this. So it's several branches. Here I copy pi over 2 maybe to here, minus pi over 2. Here you'd have another vertical asymptote like this. And then the tangent is just a collection of branches like this. And here we didn't look at this in the unit circle because it's a tad trickier, but now you can also discover the symmetry of the tangent. It's in fact easier if you have an alpha here, like this. You do your vertical copy line, so to speak, that generates more solutions. And then you see you have solutions here. The important next solution is here, and here you might already anticipate or see, you just jump by pi to the right. So here is alpha plus pi. And that gives us also the symmetry for the tangent. Tangent has a symmetry of tangent of alpha is the same as tangent of alpha plus pi, or in degrees, tangent of alpha is the same as tangent of alpha plus 180 degrees. All right, we use that in the lessons to find all solutions for x between 0 and 2 pi. So that's usually the classical exercise. And here I'm just gonna do one example. For instance, if you have sine of x is 0.5, you can convince yourself with the calculator that x then is sine inverse of 0.5, which should give you, if you set the calculator in degrees, it gives you 30 degrees, and 180 being pi, 180 by 6 is 30, so here 30 is pi over 6. If you set it in radian, you got the pi over 6 directly. And then this would be x1. x2, using the symmetry of the sign, is pi minus this solution, minus pi over 6. So that's 5 pi over 6. And those are all the solutions for this in between 0 and 2 pi. You can solve the other exercises, work exactly the same way, just with the other symmetries. All right, then we used all of that to set up sine rule and cosine rule. And the cool thing about that is this works now for an arbitrary triangle, not only for right-angled triangles. So here it maybe looks a little bit like a right angle, but it shouldn't. So here none of those three angles are 90 degrees. And then we proved the sine rule. The sine rule is just that always the ratio between the side and its opposed angle. So here, if I also draw the sides A, C, and B, A is exactly opposite of alpha, C is opposite of gamma, B is opposite of beta, and those ratios with the sine added are always the same. So A over sine of alpha is B over sine of beta is C over sine of gamma. And you saw in the lessons that, well, you either focus on maybe this, or this is equal to that, or this is equal to that. Depends on the exercise, you just pick and choose. What you might, or what you have discovered in the lesson 2 is that with this, if you're given all three sides, you're a little bit stuck, because here if I give you A, B, and C, you can construct the triangle if it's possible, but there's no way to obtain the values of alpha, beta, or gamma. Note that here, no matter what equation I take, if I take this one here, alpha and beta are known. If I take this equal to that, alpha and gamma are known, and here beta and gamma are unknown. So I always end up with one equation, but two unknowns, and that's just not solvable. So here that would be the answer to this task here. It's just not possible to calculate alpha, beta, and gamma with the sine rule if you're given the sides A, B, C. And that's why we have the cosine rule. So in a general triangle sketched as before here, you have three versions of the cosine rule, namely c squared is a squared plus b squared minus 2ab cosine of gamma. B squared is equal to a squared plus c squared minus 2ac cosine of beta, and a squared is equal to b squared plus c squared minus 2bc cosine of alpha. You can learn them by heart, you can look them up in the formula book. What I would advise you is always remember you have always one side squared equal to the other sides squared up and added up, and then minus 2 times the two sides again, AB, times the cosine of the angle opposite of your side here. So gamma is opposite of C, beta is opposite of B, alpha is opposite of A. So that's the structure of the cosine rule. Depending on the context, you might set up one or the other. So note that depending on the exercise, it's best to set up one of the three. Sometimes there's a clear choice which one you have to take. Sometimes any of those work. Here with remark 4.1, you can think about it briefly, maybe you remember it. If any of the angles, alpha, beta, or gamma, is a 90-degree angle, so let's say here, or here we have 90 degrees, or pi over 2, remember that cosine of pi over 2 or cosine of 90 is equal to 0. So this cancels the whole part here, either this one, that one, or that one. So the equation sort of devolved to c squared equals a squared plus b squared, or b squared equals a squared plus c squared, or a squared equals b squared plus c squared. And these are, of course, all Pythagorean theorems, and as they should be, because if we have a right-angled triangle, the Pythagorean theorem is true. So the cosine rule, in essence, is a generalization of the Pythagorean theorem. Then you have certain trigonometric identities. One we've already discovered at the very beginning, that tangent is sine over cosine. Here what you can do is that if you have here your unit circle again, you have your point with the associated angle. What you can do here is you can imagine you prolong this here up until this, it hits this vertical line here, giving you a new triangle, and that way here you know that now here orange is sine of alpha, blue is cosine of alpha, here cosine of alpha, and because, now careful, this triangle here, the small one, and the large one here, they are similar, meaning the large one is just a blown up version of this one here. That means the sides are similar in ratio. So if I take orange divided by blue, or vertical divided by horizontal, then this should give me the same thing as when I do this in the large triangle, this vertical divided by that horizontal side. And note that if I do that, I have sine of alpha divided by cosine of alpha in the small triangle. And in the large triangle, here you can think about what happens. What you should realize is that this here, the horizontal side in the large triangle, is equal to 1 because it's part of the unit circle. So here it's bound to be tangent of alpha. And this is how you rediscover this identity in the unit circle, or what it's sort of the relationship is to the unit circle. What you just need to remember really is that sine divided by cosine is tangent, because you use that a lot. There are a lot of sort of tangent tricks that you can do if you have sine and cosine in equations. You see that in the exercises that we solve in the lessons. Last but not least, you have the trigonometric Pythagoras. Here you have another kind of identity that holds for any value of alpha. So you do your setup again with sine of alpha, cosine of alpha, and the unit circle. And here what you need to realize is pretty simple, just that, well, we've always looked essentially at a right-angled triangle. And in a right-angled triangle, we know that the Pythagorean theorem holds. So here in our triangle, we know that the square of the sine is sine squared of alpha. You can also write it as sine of alpha squared, but that's the same thing. Mathematicians just like this version a little bit better because you don't have to put those two brackets here. So you have sine squared plus the other side squared is, well, cosine squared is equal to 1 squared. That's the hypotenuse, but that's just 1. And this is the trigonometric version of the Pythagorean theorem. And another identity that is often very useful, for instance, it allows you to solve or replace sine squared with 1 minus cosine squared if you carry that over to here. or cosine squared with 1 minus sine squared. There are different things you can do. All right, so that's the whole trigonometry script, a little bit of a speed run of it, but it's also more meant to give you a brief revision, be it for the matura or for an exam, or if you've forgotten something or you weren't in the lessons. That's just the whole script filled out.